Okay, strange. Why it stopped? Like we didn't cross hour, right? Like we didn't really cross the time yet. Yeah, this is like just half an hour, right? Okay. Okay. Yeah. Thanks for letting me know. Okay. Yeah. Okay. So the intuition that we have is like as z is increasing. Okay. Since this is 1 1. This phi function is making sure that it's also kind of like increasing only. Okay. Because it cannot like come back, because the moment it comes back, it will no longer be 1 1. Okay, you see the intuition that is happening here. So the fact that in the original z variable, this is how like increment of z is. Okay, and the function was somewhere like this. Okay, I mean function may not be convex or whatever. Okay, but function is something like this. Function itself may not be like 1 1. We are not worried about f right now. But what we are trying to say is, as z is increasing, the behavior of the function is like kind of like this. But if I've done a transformation of my z, okay, via some map phi, the behavior of this will be like similar, because xz is increasing, phi being 1 1. So as z increases, phi being 1 1, phi of z is increasing. Okay, if it is not, then it's not going to be 1 1. Okay, or at least it's like it should. I mean, if it makes it flat, then it's a constant function anyway, right? So phi of z is some constant of z, so that's fine. I mean, then there is like no change in optimal value anyway, right? So the intuition behind this is like, as z is increasing, phi being 1 1, this is ensuring that phi z is increasing. So if phi z is increasing and fi is the same fi, so whatever its behavior would have been on z, its behavior is like similar on phi of z. You see the intuition here. So as z was here, let us say, okay, and z was here and so on. So if z value increased, the phi value did like this and f value did like this. So same thing will have, because phi is ensuring that as z is increasing, so phi z will also keep the function values uh, intact in that sense. Okay, and then
Sir,
yeah.
sir, as Z is increasing and phi being 1 1, phi
Hmm.
can also be only decreasing, right? Like
Yeah,
why only decreasing?
yeah, it could be. It could also be decreasing. Yes, but the point here is like I can always recover, even if it's even if it's like monotonically decreasing. The point is like I can recover from there. Okay, but in general, if it is increasing and decreasing, that's the place where I get confused, because that's when like the optimal point may not necessarily map with the optimal point of the jet star. Okay, so it may be increasing decreasing also. um, so so the point here is like 1 1 functions maintains the like it does not destroy the structure of maxima and minima. Okay, that's the most important point. So it does not destroy the structure of maxima and minima. Okay, so like as you said, like if it is decreasing, then yeah, so maybe the maxima is going towards minima, but it's going to find something, and then I will like change back. Okay, so I will like I can transform back to my original problem. There is still a possibility that so maxima may look like minima, but still I found something, and from there I can just revert back. So that's the point. Okay, so it could be decreasing. It's a good point, but the point here is like it's a inversible. Like I can go back as long as I can go back. It's fine. So 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 if we have a condition like this, it's 1 1. Okay, so either it looks like this or it looks like this. Okay, kind of monotone. Okay, but the important thing is that it doesn't do like this. So the maps like this will preserve the critical points. Okay, so it will preserve the critical points. Okay. So if we consider problems like this, okay, where we have done a transform of Z by a 1, 1 function phi, and similarly we did this for the equality constraints, and then consider this function where we have this transform, and then we got this f tilde, fi tilde, hi tilde. Okay. So if Z solves above, so if Z solves the above problem, this one, okay, then x equals to phi of Z will solve the standard optimization problem. Okay, so if x solves, so the standard optimization problem was again like minimize f naught f naught Z. Let us say, since we are talking about Z, and then subject to fi Z is less than equal to 0 and hi Z is equal to 0. Okay, so this is the standard optimization problem. And so what this is saying is like if Z solves this, so if there is a Z for which I get the minima, then if Z solves this, then, and so if there is a Z star, then phi of Z star will solve this problem. Okay, so phi of Z star will solve this problem. And similarly, if x solves the original problem, okay, so if x solves the original problem, so let us say yeah, so x solves the original problem. So let us say x star we found for this problem. Then to go back here, I will do phi inverse of x star to get a solution for this problem. So in this case, now Z star will be this phi inverse of x star, phi inverse of x. Okay, so so this is the so they are equivalent again. Okay, if I am given a 1, 1 function, and then I yeah, so I'm not showing you any concrete example right now, but this is something like you can like you can see this with some examples I will put in assignments, let us say. I don't know if you have right now I have an example, a concrete example. So but this is the fact. Okay, so this is how like one can go from one problem to another as long as phi is 1, 1. Okay, so they are equivalent problem. Okay. Another case is like phi naught is like monotonically increasing. This is a different case. Like we saw, phi being 1, 1 could be increasing, or it could be decreasing. Okay, so that's the case that covers both increasing and decreasing. But now what we are talking about is only increasing case. Okay, and so phi naught is psi naught is the first one, right? So that will most likely apply to the objective function, right? That's why it's the subscript, it's not. So let us say this is monotonically increasing, and the remaining ones, psi 1 to psi m, satisfy this. So if psi I u is less than equal to 0, if and only if, okay, if and only if u is less than equal to 0. Okay, so psi I less than equal to 0, if and only if u is less than equal to 0, and the remaining ones like m plus 1 to p, they satisfy psi I u is equal to 0 if and only if u is equal to 0. Okay, so let us say these conditions are given. Then if we define fi tilde as this, so this includes the objective function as well. Okay, as this. So psi I. So remember in the earlier case we had like in the earlier case we had transformation of the variable. Okay, now what we have is like transformation that is applied on the functions itself. Okay, on the FIs. Okay, so there is a difference here. So and then so we define this f tilde and hi tilde using this additional mapping of the FIs and additional mapping of the HIs. Okay, respectively. Then the associated problem is this, right? So then we, let us say we want to solve this, right? So in this case. Okay. Yeah. So so these are all also equivalent. That's what I'm trying to say. Okay. So I have not written down explicitly here. So the solutions that we get for this will be the same as the solution that we get for the standard optimization problem. Okay. Standard optimization problem. So a standard optimization problem was minimize f naught x subject to fi less than equal to 0, hi is equal to 0. Okay, so this was the standard optimization problem. So in this case, again, if these conditions are satisfied, then whatever x star I get here will be the same x star that I get here. Okay. So these things will guarantee that. So in this case, x star will be the same. Okay, x star will be the same, but the optimal value will change. Optimal value will change because these guys are mapping this. So this objective function has changed now, right? But the place where you will get the optimal point, they are going to be preserved, and this is all because of this monotonically increasing function here, psi naught being monotonically increasing. Okay, and the inequalities are not going to change because of these restrictions. Okay, so whenever u is less than 0, phi guarantees that phi u is also less than equal to 0. In other words, if fi was less than equal to 0, then psi I of fi is also guaranteed to be less than equal to 0 because of this restriction. Okay, so fi is less. So original inequalities are not changed by applying this. So this fi is also satisfy the same inequalities as fi. Okay, the less than equal to remains less than equal to. So that is guaranteed by this. Okay, and only for the objective function we guarantee that it's monotonically increasing. Okay, so it's monotonically increasing. So that guarantees that the structure that I said in the last thing, that remains preserved because of the monotonicity of this. So if I map this function to some psi I, so it is also keeping the same like structure. Okay, so the point where I get some optimal value for this guy will be the same for this guy in the transform problem. Okay, of course the optimal value is the same. Sorry, the optimal point is the same, but the optimal value is different. So this is like P1 star and this is like P2 star. Okay, so I'm not doing a concrete proof of this fact. Okay, but I will just leave it with an intuitive thing, and you may apply this in a problem. Okay, yes.
Sir, once can you explain how the objective function changed from the original and this after transforming it to psi I? Like how the optimal function changed? I mean, objective function changed. I understood the
Objective function
constraint.
change, right? Because you are mapping, right? So objective function does change, right? So it's like I mean I'm applying some psi, right? Psi is not an identity function, so it changed, right? So this is no longer the same as f naught, right? Because psi is applying on.
Okay. Yeah, I mean you are minimizing now psi I of f of xi, right, sir? Like
yeah.
psi I of f. Yeah. Then how the final optimal value get related?
Yeah, look, final optimal value is related by psi I, right? But what is most important is like these guys, I'm always solving this for x, right? So I mean here I'm solving it for f naught, and here I'm minimizing this. So what I will get after solving this is x star, and once I get x star, if you ask me to find like optimal value of this, right? So I will do f naught tilde x star. And that is indeed the optimal value that I'm looking for. So this is the P star of this problem. But the main goal is like, what is X star, right? So X star I know is like it's not changing because of the guarantee that psi naught being monotonically increasing. So this is not changing the place where the minima would be achieved even for the transform problem. The only thing is like the height may be different, but the fact that the place where the minima is not changing, that is the guarantee I have. Okay, that is the guarantee I have, and the additional constraints make sure that the inequalities are also not changing. Okay, so these inequalities don't change.
So optimal will be same in both, right, sir? X star will be same, but
X star
optimal
will be
value
same.
will be
Yeah,
like it
so
may
optimal value will be different. Yes.
So
yeah, so here the optimal value will be P star will be f naught x star, whereas here it will be f naught tilde x star. So this will be psi I, which is equal to psi I fi x star. So if psi I is some some increasing, I mean, this is psi naught, okay? So we are talking about objective only. So psi naught. So psi naught is some increasing function, right? So that's why the this won't change, right? So that's why this this won't change. So like, yeah, so I can like give you some intuition at some point, because we will be with this topic for some point. Like I can ask you as an exercise. I can already ask. I don't have like right now time to go through this, but I think you can pretty well do this. Okay, so let us say minimize, and I want to do let us say I want to minimize minus let us say I want to minimize x square minus 2, okay, and subject to let us say x greater than 0. Okay, so I'm giving you an example where you should do the practice, and let us say the psi naught I give you is, I mean, in this case there is only like two things needed, right? So psi naught I give you is, let us say, 2x. Okay, so this is a monotonically increasing function, right? Now prove this result, that the x star that you will get for the f naught tilde, right? So f naught tilde in this case will be psi naught of f, right? So psi naught of f. So this will be like psi naught of f, right? So this will be 2 times x square minus 2, right? So the minima that I have it here, I know that the minima for this is square root of 2. This square root of 2 minima, it didn't change here also. And that is happening because I took this something as a monotonically increasing function. So that guarantees me that the minima of this didn't change. So minima of this, but optimal value did change, because the minimum value of this is like 0. Okay, so 0 or yeah, so this yeah, I mean, I think let me make it more. So x minus 2 whole square. Okay, so this, let us consider this parabola is a bit better. Okay, so this will be 2 of x minus 2 whole square, because I chose a simple example for explanation. So what I see is like this guy is like greater than equal to 0, and minimum is 0 is achieved at x equals to 2. Okay, so that is very clear just by looking at this. So this is the constraint, and so on. And here also the minimum still remains 2. Although I have done a mapping via some increasing function, monotonically increasing function. And the point here is like this will remain the same for all. Like even if I do psi naught to be some other monotonically increasing function, let us say e to the x, like e to the x curve is like this, right? So this is the exponential. So even if I do exponential, right? So f naught tilde in this case will be exponential of x minus 2 whole square. Okay. So again, the minimum value of this guy is still going to be 2. So x star is still going to be 2. And all this is happening because of the monotonicity. Okay. So these are the examples. I will put some concrete example where you will see non-monotonic, and then you are doing map, and then the optimal point is no longer preserved. Okay, so I will give one practice example in the assignment. Okay, but I hope the intuition is clear. Okay, that this is guaranteed due to the monotonicity of this psi node. Okay. Okay, so so one of the questions that we ask is it possible to replace the inequality constraints by equality constraints and non-negativity constraints? Okay, so this is just like a fun question we are asking right now without even thinking whether it will be immediately useful. Like just think of this as just a standalone quiz. Like, can we do this, right? Without even asking why or how. I mean, why, right? So how we can do this is the question. So the question is telling us this is the inequality constraint. The question is focusing on inequality constraint. So can I replace this by equality constraints? So can I replace this by equality constraint? And let us say and, okay, so some of you see this as plus, right? So and non-negativity constraints. Okay, the non-negativity constraint is this. So can I write this inequality as a combination of equality and like greater than equal to constraint? Okay, so that's the question here, right? I mean, this may look a bit like an absurd problem right now to you, because you may say, I multiply by minus on both sides, and I can write this as minus x, and this does indeed go to this greater than equal to constraint, although I don't have any equality constraint. So that's fine. Like I did not bring any equality constraint, but I immediately satisfy this criteria, right? So, but that's not the point. Like it's just telling us that we will introduce some variables, and we will have equality. We will make this equality. Okay. Yeah. So let me phrase this correctly. So how should I introduce the variable such that with these guys I have equality with these guys, like fi, okay, and you may do something, I don't know, okay, but these fi guys will satisfy the equality, and you are allowed to have some greater than equal to inequality, additional greater than equal to equality, okay, and remaining can remain same, okay. So this is the more concrete question that this quiz is asking, like how can I change this inequality constraint to the one where FIs are involved, but it becomes equality, and I am allowed to add or subtract whatever here, some additional variable. And then I introduce some additional inequality, which could be like greater than equal to now. Yeah, okay, that's the question, okay. And there is a reason why we are looking for this. Yeah. So
Sir,
you have answered?
like we can add, yeah,
Yeah,
like
you can
I
add
think
some
so.
variable, right?
Yeah, and that variable will be greater than equal to 0, right?
Yes,
So it is
because this is,
non-negative constraint.
yeah, so that will be non-negative. So the idea here is like, since this guy is less than equal to, so there must be some value I will add such that it will become equal to 0. So let us say that is like Si. So if Fi was strictly less than 0, then there must be some additional Si I should put such that it becomes equal to 0. And that Si must be something positive, right? So that's why we have this Si greater than equal to 0. So there is a reason behind this. It will not be evident right now, and I'm not going to say much about this, like why are we doing this right now, but we will make use of this later on. And these are called slack variables. Okay. So SI are called slack.
Sir, I had
Yeah.
one question. So
Yes.
in this, is it necessary that SI be a number or it could be a function of X? Because we have to
SI
satisfy.
is number here, right? Yeah. I mean, it number would be enough because, yeah, because okay, yeah, good question. Yeah. So it would be a number or a function because FIs are variable, right? So it has to be like variable as well, right? To
Right.
make it 0. Yeah, it has to be variable actually. I mean, it should be a function. I mean, so SI must be function because FI x being less than equal to 0, this is saying that it's is less than 0 for all x, right? So if that is the case, then SI must be also a function of x, okay? So that should compensate for each x and then it should make it equal. Yeah, so that's a good point. Okay, so SI has to be also a function of x, not just some variable. Just some variable won't work. Okay, because f is a variable. Okay, I mean f is a function of x, so okay, it varies with x. Okay, so the key observation is that is fix less than equal to if and only if there is an si greater than equal, and this is what we described right now. Okay, so to be more precise, we should put x actually. Okay, it's like implicitly assumed here. Okay, okay. So here SI are called the slack variables. Okay, so this is the term that you should remember this. We will use this slack variable at some point. So, and is this equivalent? Yes, this is exactly equivalent problem. Like we don't even have to, like we did not change anything. Right? It's just we introduced slack variable. So this is not going to change anything. Like feasible set remains same, optimal point, optimal value, all will be same. So obviously this is still an equivalent problem. Okay. Now we have seen. So what? Yeah.
Sir, won't it be Fi plus Si equal to 0? Fi again less than equal to?
Yeah, so there is a wrong here. Yeah, you're right. Okay, thanks for the correction. So this is like equality here. Okay, so that's what we are claiming here. So this is the equality here. and then this slack variables are like greater than equal 0. Okay. Okay, so what we have seen so far is just optimization problem in standard form. Optimization problem. Okay, so we have seen so far, and this is the this is the form we have seen so far. Optimization problem and in standard form as well. Standard form means that right hand side must be 0, always inequality, and so on. Okay, this is what we have seen. And now we are coming to some specific case where we say convex optimization problem. Okay, so remember we spent so much time on convexity and so on. So this is the time like we are now like narrowing down, okay, on what are the specific types of problem like convex, and then like we will see many types actually. Okay, so let us start with specific case where we have convex optimization problem. Now convex optimization problem, what is the specification, right? How does it become specific from coming from general case, right? So that's what we are trying to figure out. So it's looking same, but here we observe the difference, right? So equality constraint is specific here. It's always like this form, right? And here we allowed equality constraint to be very generic, okay? So that's what this point is saying. The equality constraint are all affine constraint. We know that this is an affine function, right? So this is the one big change. And another restriction you will see is that these FIs are convex, right? So this objective function and the inequality constraint functions are supposed to be convex now. Okay, so that's how we are getting into convex optimization problem. So there may be questions in exams where you will be given, and then you have to tell whether it may be objective question, and then you have to really ask whether it's a convex or non-convex. Whether it's a convex optimization problem or not. Okay, so these are the conditions. Okay, if you would have treated this as HI also. Okay, and the fact that HI is affine, so HI is affine. And naturally, affine is also convex. So HI is convex as well. So you can say in general, convex optimization is an optimization problem where all the objective and inequality constraint functions and the equality constraint functions are convex, and moreover, specifically HI must be an affine function. Okay, so there are other ways to put that there, put this. Okay, so this is convex optimization problem. Okay, and so that's it. That's what we have to remember. So consider this example where you have this. Okay, so this is the maximize problem. So first of all, notice so far we were discussing minimize, but this is like maximize. Okay, and then this is subject to, and this is the inequality constraint, and there is only one inequality constraint function, and we have a equality constraint function which is denoted by H1, and there is only one equality constraint. So we know that it is in standard form, right? So this is in standard form. Like we do include maximize also in standard form, given that it's very easy to change to minimize. Just I put minus. So overall, it is in standard form. Okay, bearing maximize, minimize, because that usually doesn't matter. It's just one step to change to minimize, right? So this is in standard form in the sense that we have this objective function specified. We have the inequality constraint with right hand side 0, and this is indeed the less than equal to. So all this is verified. This is also checked that right hand side of the equality constraint is 0. So this is indeed in standard form. That's the first check. Okay, now is this problem a convex optimization problem, right? So that's the question I'm asking. Like, is this a convex optimization problem? Yes or no?
H of X is not affine, right? So
yeah, so
it's not defined in.
Yeah, so observations for this question is H1 of X is not affine. Are there any more other reasons that that you may apply? What are the other conditions for convexity, a convex optimization problem? So all has to be like convex, right? So is F not convex? F not convex? What do you think?
Yes, sir.
F not X is convex, right? Which test you will do to check this?
So this is the square of the norm. So norm is always convex. So
yeah. Okay. So So this is like a square of a norm. Okay, so this is like norm of x squared. Okay, so 2 norm of x squared, and norm is always convex. So this is checked. Okay, so this is okay. Are these fi f1 and f1 must be like convex, right? So is this convex? Is f1 convex, right? So that's another question that we are asking, right?
Sir, we can construct Hessian matrix and check it.
Yes. So you can construct Hessian matrix. So it may not be very obvious. Okay. So construct Hessian H and check X transpose H X is greater than equal to 0 for all X. Okay. So this is something we may have to do it offline. Okay. So to do this. To do this check. Okay, most likely it's not. Okay, the form of this is making it look like it may not be. Okay, so okay, I mean, is it or is it not? Okay, I should like revert back. Like yeah, so this is something like you may want to check. But like, is this not like is this not just a like? Can we not simplify this? Like, is it really that complicated? Like x1 by 1 plus x2 squared is less than 0. What is the, how does it simplify?
x1 less than equal to 0 because denominator always positive.
Yeah, so this is same as x1 less than equal to 0 because I can also divide x1 by some positive number because it is positive. Okay, so the main observation is that it's positive. So these are equivalent actually. So okay, so remember I'm still not claiming that x1 by 1 plus x2 square is convex. That is still a question mark. But what I'm saying is like this inequality is just a like camouflage, right, on our eyes because this inequality is nothing but this inequality. Now if I look at this guy, this is convex surely. Right, this is like a linear even. So there is a lot of camouflage happening here, right? So the idea here is like a non-convex looking problem can be transformed into convex. Like I already gave you a hint. Now you can already see what could be done for H1, right? Because H1 so far is not affine, like one of you said. But can I not simplify this such that it does look like affine, right? So how should I simplify H1? So H1x, this is the inequality x1 plus x2 square is equal to 0. This is equivalent to. So can you tell? Hello, are you there?
x1, x2 equal to 0.
Yeah, so x1 plus x2 equal to 0. Thanks. So this is same thing as this, right? So yes, all this is camouflage here, right? So these are just so you have to see this problem when you are working with optimization problem. You have to know how to simplify things. I mean, initially you may panic, but maybe there is a way to simplify, and it looks like some. And convex is very good thing, right? We have seen this intuitive thing a couple of times now. So in this case, so as such, it is no. So the answer, what you said, is correct. But then we can rewrite this in this form. Okay, and this is now a convex optimization problem because this is now affine. Okay, so this is inequality is fine, and this is like convex. So F1 is convex, and this was convex anyway. So this is what we needed to be a convex optimization problem. Okay, so now let us. Now that we have a general convex optimization problem, okay, now we may prove some interesting results. For instance, a local optima in a, let us say in general case, constraint optimization problem, not just unconstrained. Unconstrained is a simple case, okay? So constraint optimization problem, local optima is nothing but a global optima, okay? So that's something like we may want to prove, okay? So local optima is nothing but a global optima in a constraint convex optimization problem. So what do we do here, right? So let us prove this result. Okay, this proof requires some effort. So let me do this proof. So let me do this, I think, here. Okay, so in the scratch space. So what we are trying to say is that for convex optimization problem, so here I write the statement for convex optimization problem, local optima is global. Okay, so the thing that is a bit tricky part here is the constraint here. Okay, so the constraint part is a bit tricky part here. Otherwise, for the unconstrained problem, like it's the proof is rather simple. Okay, for the unconstrained problem, what is the proof you can think of, right? So for the unconstrained problem, you can use those criteria that we had, like the first order condition and then the second order also, assuming that it's differentiable. Okay, so then it's like pretty straightforward. Okay, so let us try to prove this from the basic principles, and suppose that yeah, so suppose that X is locally optimal. So let us suppose that X is locally optimal. So suppose that X is locally optimal. Okay, locally optimal. So this implies that X is first of all feasible, and yeah, so for this X I get the optimal value, right? So optimal value will be f naught of X. Okay, is so for that X I get the infimum of this set f naught Z, such that Z is feasible, and norm of Z minus X is less than or equal to R. Okay, so we are talking about local optimality here, right? So we are looking at some R radius ball around Z. Okay, so this is the Z, and then this is the and then this is the radius R. Okay, so among all the, so in this ball, okay, we are talking about what is the minimum. Okay, that's the meaning of locally optimal, right? So locally optimal means that for a neighborhood in this area, okay, in this ball around Z, okay, which is radius less than or equal to R. Okay, I get the smallest possible value, which is f naught X. Okay, so this is for some R greater than 0. Okay, so let us prove this by contradiction. Okay, so assume on contrary. Okay, so assume on a contrary that suppose that X is not globally optimal. So suppose X is not globally optimal. Okay, so locally optimal we have said. Okay, so there is a neighborhood and then X is the boss there. Okay, in other words, X gives you the minimum value there in this R ball, and what we are saying is like X is not globally optimal. This means that there will be some other Y outside the domain. I mean outside, not the domain, but outside this R ball, where actually the function will obtain the minimum value. Okay, but in this ball, the locally X is minimum, but globally not, because there is some Y for which f naught Y is even least. Okay, so that's what we say. So X is not globally optimal. So that means that there is some Y. There is a feasible Y. So there is a feasible Y. Okay, which is feasible Y for which for which f naught y is less than equal to f naught x. Okay, so it's not globally, right? So there is some y which is outside, and for which it is like we do get a least value as well. Okay, so and since since x was the locally optimal, so naturally like y will be some point outside. So the distance of y from x. Okay, so I think we should make a ball around x, not around z. Okay, and z are the arbitrary points because z is the arbitrary points here. So these are the z here, and x is somewhere here. Okay, and if I take a neighborhood around this for other points, it's like I'm getting greater values of f naught. Okay, okay, the center is x. Okay, not z. Okay, so what do we know? So y is since outside because x is the locally optimal. So so if x is not locally optimal, then I got y for which I get a optimal value. So this y must be outside. Okay, so this implies, so evidently y is distance of y from x is larger than the radius r. Okay, so this must be greater than, right? So evidently the norm of y minus x, okay, is greater than r. Okay, okay, so so that's the thing. And now consider the point z. Remember, we are assuming the contrary, right? We are assuming the contrary, so we have to get some contradiction. Okay, so my plan is to produce some point z, let us say, okay, for which it will contradict that it is even locally optimal. Okay, so that's my overall top level plan that so I will use convexity definition and so on to arrive at that, because what are the things I'm given is like this feasible set, the constraint of problem functions are convex and so on. So because this is a convex optimization problem, so those basic assumptions I'm given. Okay, so using all those, like I have to arrive at contradiction. So my plan is to produce some some z which somehow lies here, and it achieves a even smaller value than fx. Okay, so that's the overall plan. Right now it may not be very clear how I will achieve that. So let us see the proof. Okay, so consider the point. You look here, this z is arbitrary, and here the z I am choosing is some fixed z. Okay, so this z has nothing to do with that z. Okay, so consider the point z given by z is equal to 1 minus theta x plus theta y, and theta I choose is this. So this will look artificial. That's how it is, but all this is carefully chosen so that I will arrive at a contradiction. Okay. Okay, so if you consider a point like this, so what is this like point, right? So this point is like somewhere like it's a line, right? We know that, but it depends. Like I mean, if the theta varies from 0 to 1, then it would have a line. So, but one thing we know for sure is that z is lying somewhere on this line. Okay, depending on what is this, right? Okay, so let us see, like, so will z lie inside or outside, right? So that's already a valid question, right? Here is a r, and y minus x I know is like greater than r, right? So this is like greater than r. So I already know that this guy is like what, less than half r by 2, right? Right. So this guy is, so we can already write this, right? So y minus 2 is greater than r. So denominator is greater than r. Right, so this is like less than half. Yeah, so this is like less than half. I mean, that's what we can conclude right now. Okay, using this inequality, this is what we can conclude so far. So it's like midway will be half. So this theta is half. So we are like less than, and we are starting from where? Theta 0, we start from x. So from x we are, so we are like closer to x. So z is like somewhere here. Like this is still not saying anything because yeah. So this is still not not saying anything, right? Yeah. So this is still not saying anything to us. Okay. So this is the information so far we have. Z is like some point on here. Okay, Z is some point on the line joining y and x. Okay, so let us proceed with this Z, and can we like see a contradiction coming already, right? So that's the question we are asking. Okay, I have another scratch space, so let us do this here. What is the next thing to do, right? So the next thing to do is like I will look at like Z minus x. Okay, so this Z is like this Z. Okay, so Z minus x. So let us look at Z minus x. So look at Z minus x. And what do we have, right? When we look at Z minus x, well, Z minus x is equal to minus theta x plus theta y, right? Because Z minus x, Z is this. So if I subtract x from here, I will be left with minus theta x plus theta y, right? So minus theta x plus theta y, that's what I've written here. Now look at, so we have, now I will look at the norm, right? So norm of Z minus x whole squared. So norm in terms of the inner product we can write, so Z minus x transpose Z minus x. So this is nothing but minus theta x plus theta y transpose, and then again minus theta x plus theta y, right? So this is equal to theta, how much? This is equal to theta square and y minus x transpose y minus x, right? So this is like a theta square and norm of this is like theta square and norm of y minus x whole squared, right? So y minus x, theta square was theta square is r square by 2 square y minus x. Okay, so theta square is r square by 2 square and norm of y minus x squared. And then we have this term y minus x term here, right? So y minus x to norm, and then this is squared. So this gets cancelled. Okay, so this is like r by 2, and this is like less than r because r is some positive, right? It has to be positive. Okay, for x to be locally optimal, right? So so this is like the, what does this say, right? Like we started from here and we ended here. So where is this Z now? Distance of Z from x is less than r. What do you conclude? So what do you conclude?
That Z lies inside this circle.
Yeah, so Z lies in that circle. Okay, so let us call this ball radius r centered at x. So if you, in case you study real analysis and topology, this is how we define a ball centered at x with radius r. So this implies that Z is in this ball centered at x and radius r. Okay. Okay, so that's one information we got. Like with this choice of Z, Z is in the R ball. Now my original plan is to prove that f of Z is even lesser than f naught of Z is even lesser than f naught of x, and then it will disprove that x is locally optimal. Hence it will disprove. Hence our contradiction has to be our assumption on the contradiction has to be reversed. In other words, we have to assume that we have to like conclude that x is globally optimal. Okay, that is proof by contradiction. That's how it works, right? So next step that is left for us is to prove that f of Z, f naught of Z, is actually lesser than f naught of x. Okay, so that's the part left. Okay, so Z is in this. So Z is in this, and you know, another thing to note is like the feasible set is like convex, right? So if the feasible set is convex, so Z will actually lie in the feasible set. So feasible set is convex. Implies Z, which is 1 minus theta x plus theta y, belongs to the feasible set. Okay, I did not write like what is the feasible set, so it's like belongs to the feasible set, because as a set, feasible set is convex. Okay, so okay, so what do we do next, right? So we have to like find f naught z, f naught of z, right? Okay, so this is the line joining x and y. So if I apply f of z, so f of z is like f of 1 minus theta x plus theta y. Now due to convexity of f naught, right? So these are all f naught. So this is the function value on the, this is the curve value, right? So the curve remains below, right? So it remains below the line joining. So this will be 1 minus theta f naught x plus theta f naught y, right? And what we know is like f naught y was greater than or equal to f naught x, right? So this is like 1 minus theta f naught x plus, I mean, this will be less than equal to, right? Yeah, so this will be further less than equal to, because f naught y was greater than or equal to f naught x. Remember, because that's the thing, right? So this is the one, right? So f naught y is less than or equal to f naught x. So this theta f naught x. Okay, so like theta, like f naught x is greater than or equal to f naught y. So I have substituted this by greater quantity, so it remains greater or equal. Okay, and then this gets cancelled. So this will be just f naught x, right? So this will be just f naught x. So what do we conclude from here? We conclude that we got a z. We got a z for which I am getting a lesser value, okay, than f naught x. So this is contradicting the fact that f naught x was the locally optimal, okay, because I have found another z which is in the R ball. So this implies z is in the same ball. Okay, z is feasible because it's a convex combination of the points in the feasible set, and f naught z is less than or equal to f naught x. So this implies it contradicts that x was locally optimal, because when x is locally optimal, it has to be like less than the function value had to be less than or any other value in the neighborhood, but we have contradicted that. It contradicts that x was locally optimal. Okay, so hence our assumption must be wrong, and our assumption was not globally optimal, right? So hence our assumption is wrong. So hence our assumption that x is not globally optimal is wrong. Okay, so that's how the proof by contradiction works. That is, the not of this is like that is x is globally optimal. Globally optimal. Okay, so that's the proof of this by using the contradictory by using a proof by contradiction, right? So the reason why we have to go through this long route is because of this set and so on, and also remember that nowhere we used any additional requirement on differentiability. So this proof is very general. Okay, this proof is general because we proved it by a first principle. So this holds for non-smooth convex function as well. Okay, so the functions like this. Okay, so these functions are not differentiable. Okay, at these kinks are there. So this result holds for any constraint convex optimization problem, possibly non-smooth. So we never used any gradient. Okay, so that's why this proof may be longer, but it's more general. But if it was differentiable, then things become a little bit easier, right? Because we can use that first order criteria, right, where we have the gradient case, right? So we can what was that? Fy is greater than equal to fx plus gradient of fx y minus x, right? So this holds for all x and y. So f is differentiable plus convex. So if it is differentiable, then we talk about gradient, and this holds. Now x locally optimal implies globally optimal if you assume the differentiability just by using this. So if x star is locally optimal, so in the optimal case, we also know that this implies the gradient must become flat. That's the condition of optimality. So gradient of f x star is 0. So from here, so from 1 implies, so fy is greater than equal to fx star. Okay, and this guy is 0 because grad f star is 0, and this is true for all y. So since this is true for all y in the feasible set, okay, whatever the domain and so on, so feasible set. So this implies that x star is globally optimal because f star is less than any function value. Okay, so this implies x star is globally optimal. So if you assume the differentiability, then it's just a few steps and you prove this result, right? And the proof that we did was longer, but it's very general. So that's why we did this. Okay, now another thing is like if f naught is a convex optimization problem and it's differentiable, then the point x is optimal if this happens. Okay, so here we are assuming that's convex and differentiable. So these are the 2 points. And then the claim is that x is optimal if this happens. Now this should be possible again from what we have written before. Let us see this, right? So fy is greater than equal to fx, the first order optimality, plus grad fx transpose y minus x. Now one way should be like easier for you to prove, right? So what this is saying is differentiable, then the point x is optimal if this happens, right? So this is like greater than equal to 0, right? So look, if x is optimal, then if x is optimal, then what we know is like this is like the, so if x is optimal, then what we know is like fy is greater than equal to fx. So that's the definition of optimality for all y. Now, if that is the case, then what can we conclude about this, right? So if fy is greater than equal to fx, so it's like, yeah, I can write this in simple form, right? So b is greater than equal to c plus d, and b is given to be greater than equal to c, right? So what can you say about d? Right. So what can you conclude about D?
D is greater than 0.
Yeah, D is like greater than equal to 0, right? So,
Sir, if this sign is there, won't it imply that D is less than equal to 0? for if B is greater than C and B is greater than C plus D. So if D is less than equal to 0, in that case, won't this optimality hold?
Yeah, so this is the case where like B is yeah. Are we missing something more here? Yeah, that's a good point. So if it satisfies one, then yeah, so other way seems to be trivial actually, right? Okay, let's see. Because if this satisfies, if X satisfies this, then the other way, okay, let me do that. I will do it here, okay? So let us try the other way, right? So suppose X, so we are running out of time, right? So suppose X is in X. So X is the feasible set, okay? So I use this feasible set. So X is in X and satisfies, let us say it satisfies the given condition, okay? So it's like both ways, okay? If then the other way could be like straightforward, right? So if this and it satisfies this grad f naught x, so grad f naught x transpose y minus x is greater than or equal to 0. Then from, and since f is convex, since f is convex and differentiable, first order condition gives us fy is the one that we wrote before. So everywhere it's f naught, okay? So f naught x transpose y minus x. So this is what we have. So other way, what do you think? So this is given to be greater than or equal to 0. Right? So this guy is greater than or equal to 0. So what can we conclude about? So does this imply that fy is greater than or equal to this? Can we conclude from here?
Yes, sir.
You can conclude here it's safe,
Yes.
right? Yeah, because we are dropping a positive term. So we are dropping a positive term, dropping a positive term keeps the inequality, Okay, so this way it was fine. So if it satisfies this, then that condition does imply that x is like this implies that x is optimal. Okay, when we say optimal, it's like globally optimal. Okay, because it's convex anyway, so local is global anyway. Okay, so we just talk about optimal. In the convex case, optimal means like globally optimal. So one way we did, right, and we are actually in time, right? So we can continue the second part in the next case. Like the other way is, I think we have to think, right? So other way would be like if this is convex, then it should satisfy this inequality. So this is the proof we will do in the next class. Okay, then so let us stop here, and I will be here if you have some doubts or question. I will be here for a couple of minutes. Okay, so I will stop here. I will stop the recording now.